In this section, we're going to talk about weak bases. Bases react with water to produce a hydroxide ion. Here we can see the weak base NH3 in water H2O to produce the hydroxide ion OH. Even though NH3 does not have the hydroxide ion, OH- in its formula, it is a base according to both the Arrhenius and Brønsted-Lowry definitions. Let's take a look at the general dissociation equation for a weak base, where we have B- in water to produce a conjugate acid HB and the hydroxide ion. The equilibrium constant expression for this reaction is Kb, the concentration of the products, HB times OH- over the concentration of the base, B-. Kb is known as the base dissociation constant. Just as for acids and Ka, a stronger base has a higher Kb value. Since strong bases dissociate 100%, their Kb values are referred to as very large. Kb values can be used to find the hydroxide ion concentration and then the POH and pH. The formula to calculate the percent ionization for a base is similar to that for an acid. It's just the concentration of the hydroxide ion at equilibrium divided by the initial concentration of the base multiplied by 100. Example 5. Calculating Kb from pH. The pH of a 0.2 molar solution of hydrazine H2NNH2 at 25 degrees Celsius is 10.9. A. Calculate Kb for hydrazine. B. Calculate the percent ionization. In part A, in order to calculate Kb, first we need a dissociation equation and an equilibrium expression. So here's the dissociation of hydrazine H2NNH2 in water to produce hydroxide ion and the conjugate acid H2NNH3+. From the dissociation equation, we can write the equilibrium constant expression. Kb is equal to OH- concentration times H2NNH3+ concentration over the base H2NNH2 concentration. In the problem, we are given the pH. From there, we can calculate the POH. 14 minus 10.9 gives us a POH of 3.1. From the POH, we can find the concentration of the hydroxide ions. So the hydroxide ion concentration is 10 to the minus POH, or 10 to the minus 3.1, gives us a hydroxide concentration of 7.94 times 10 to the minus 4. And of course, from the dissociation equation, we can see that given the stoichiometric relationship, the concentration of the hydroxide ion will be the same as the concentration of the conjugate acid H2NNH3+. I created an ice chart just to help us understand what's going on here. We start with all hydrazine and no product. Over time, some hydrazine dissociates into product, so that amount will decrease by some amount X, while the hydroxide and conjugate acid concentration increases as it is produced by some amount X, so that we have that amount X at equilibrium. And we calculated what this value was using the value given for pH to be 7.9 times 10 to the minus 4. Of course, the hydrazine concentration will decrease by that amount, but this amount is so small compared to the initial concentration that at equilibrium we just say that this is approximately the same as the initial concentration. Once we know the concentrations at equilibrium, we can substitute them into the Kb expression and solve. So I substituted 7.94 times 10 to the minus 4 for the concentration of both OH- and H2NNH3+, and 0.20 our approximate equilibrium concentration for the hydrazine, and I get Kb equal to 3.15 times 10 to the minus 6. In part B, we're asked to find the percent ionization. We know from part A that the hydroxide ion concentration is 7.94 times 10 to the minus 4, and that the initial concentration of the base given was 0.20 molar. So we can substitute those values into our percent ionization equation to get a percent ionization of 0.40%. Example 6, calculating pH from Kb. What is the pH of a 0.15 molar solution of NH3? The Kb of NH3 is 1.8 times 10 to the minus 5. All right, let's start with writing the equilibrium expression for the dissociation of NH3 in water to produce NH4 plus and hydroxide ion. And then our Kb expression would be the concentration of the NH4 plus times the concentration of the OH minus over the concentration of the base. And we're given this value in the problem to be 1.8 times 10 to the minus 5. All right, we've created the ice table. We initially start out with 0.15 molar NH3 and no product. We decrease the product, the reactant, the base, by some amount X in order to produce product in the amount X. So that at equilibrium, we have 0.15 minus X, concentration of the base, and concentration of X for both the NH4 plus and the OH minus. We can assume X is really small again, and so at equilibrium, we have approximately the same as our initial concentration of base, 0.15 molar. From here, I substituted values into my Kb expression. My value of Kb, 1.8 times 10 to the minus 5, is equal to the concentration of the NH4 plus times hydroxide ion concentrations, X times X is X squared, over my equilibrium concentration of NH3, 0.15. Solve for X and get 1.6 times 10 to the minus 3. Now, it's really important to remember in this case, what is X? In this case, X, 1.6 times 10 to the minus third, is the hydroxide ion concentration. So we use it to calculate the pOH. The minus log of the hydroxide ion concentration gives us a pOH of 2.8. And from there, we can solve for pH. 14 minus 2.80 gives us a pH of 11.20.